Complex numbers are best friend of humanity. So after the sheer success of first and second part, so I'm doing the third part right now. And in this video, we will solve this integral from 0 to pi of 1 minus a cos theta divided by 1 minus 2a cos theta plus a square. Now, how I'm going to approach this problem is, first of all, we all do know that e to the power I theta is just cos theta plus I sine theta, right? I'm going to write this cos theta as a real part of e to the power I theta. And as we know that because real part is linear, I can take it out, I can take the a inside the real part. So I'll just do it and show it to you. So what I'm going to do is, first of all, I will write cos theta as real part of e to the power I theta divided by 1 minus 2a cos theta plus a square d theta. Now I'll explain why I can take this a inside, because the real part function, let's say if I have a 1 by a real part of x1, which is a complex number, plus 1 by b real part of x2, this will just be same as equal to x1 by real part of x1 by a plus real part of x2 by b. You can verify this using the fact that real part of a complex number z is just the sum of z and its complement divided by 2. Using this definition of real part, you can try to prove this on your own. But also note that real part is linear and you can do such operations, right? But what you cannot do is, let's say if you have a 1 by real part of z, that will not be equals to real part of 1 by z. Yeah, so due to that, I cannot say also write cos theta as real part of e to the power I theta and take it out from the fraction, because this is not true. So I can just do it for numerator, of course, due to this property, but not for denominator. So yeah, after that I will just take the a inside real part, and also I can add inside the real part, so this will just be same as real part of 1 minus a to the power I theta by 1 minus 2a cos theta plus a squared d theta, right? Now again, because real part is linear, I can also take it in outside the integral, because integral is just an infinite sum, right? So yeah, from 0 to pi, 1 minus a to the power I theta divided by 1 minus 2a cos theta plus a square d theta. Okay, now definitely I have simplified the cos theta in numerator, but what about the cos theta in denominator, right? So for this one, what I can do is, I can just write 2 cos theta as e to the power I theta plus e to the power minus I theta, right? Okay, the thing is, if I do it this way, there will be 2 e's, right? So if so over here numerator also I could do the same, but that induces 2 e's, right? So I could reduce a lot of complexity by just introducing real part, but since that's not applicable over here in denominator, I have to do this, and I'll be doing this, right? So if it's possible, you can definitely use real part, but if it's not, you can also use this definition of cos theta. So 1 minus a to the power I theta divided by 1 minus 2a, and let me not write 2 actually, because that's the formula for 2 cos theta. So this is a, and we know that 2 cos theta is just e to the power I theta plus e to the power minus I theta plus a square d theta, right? Now the next thing is, you might notice that the denominator is actually factorizable. We can factorize the denominator. So we have 1 minus a to the power I theta divided by 1 minus a to the power I theta minus a to the power minus I theta plus a square d theta, right? So next step is, this will again just be real part of integral from 0 to pi 1 minus a to the power I theta divided by 1 minus a to the power I theta minus, over here if you take a e to the power minus I theta common, that will just be 1 minus a to the power I theta, right? So you see that it's clearly factorizable, and that will be helpful for us in the further solution. So we have integral from 0 to pi, real part of e to the power I theta, a to the power I theta, by now this, if we just take 1 minus a to the power I theta common, we will also have 1 minus a to the power minus I theta d theta. Now you can clearly see that we can cancel this part, and this cancellation simplifies our problem a lot. And this is basically one of the reason why I thought of doing this in the first place, right? If you just try to observe the solution, I mean observe the problem before even solving, you might be able to notice that. And yeah, due to the same reason I had done this one, so yeah, it becomes clear now why we had to do that. Now let's try to solve this. This has simplified a lot already, and it's not going to be that hard now. So we have real part of integral from 0 to pi 1 by 1 minus a to the power minus I theta d theta, right? So now what I can do is, first of all, let me use the law of indices, that a to the power minus x is just 1 by a to the power x. That will make it slightly easier to see what we have to do next. So e to the power I theta by, this is just e to the power I theta minus a d theta, right? Now you might know that derivative of the e to the power ax is just a times e to the power ax, right? Now in this case, if I make a substitution that, okay, where are the colors? If I make a substitution that this is basically our u, then as du, I'm going to get I e to the power I theta, right? And then d theta, right? If I make this as u, so yeah, so over here you might notice that du by I will just be e to the power I theta d theta, right? So this will just be du by I, and I is a constant. So over here what I want to say is, actually, if I make this as u, this entire other thing will just be du by I, right? So, and this is a constant, so this is almost like du by u. So du by u, in that case, we know that that's log of u, right? The integral. So from that, we can see that this will actually become ln of e to the power I theta minus a by I, going from 0 to pi. You see that, right? Because the differential of this denominator is just I times e to the power I theta. So since that's I times e to the power I theta d theta, e to the power I theta d theta, which is over here, is just du by I. So 1 by I is over here, and then du by u becomes ln of u. So that's clear, right? Now let's try to evaluate this. Now we know that 1 by I is just negative I. That's because 1 is negative 1 times negative 1, right? And negative 1 is just I square. So this is I square by I into negative 1. So that becomes negative I, right? So this is real part of negative I. And let's evaluate others. 8 pi, we know that e to the power I pi is just minus 1, and e to the power I 0 is just 1, right? That's because e to the power I theta, basically, if this is real axis, if this is imaginary axis, if you graph e to the power I theta, that will just, the graph will just go like this, right? Graph e to the power I theta. So you can see that this is 8 when theta is equals to 0, theta is equals to pi by 2, theta equals to pi. This is the graph that this function traces out for different values of theta. So clearly for phi, the value is like real part minus 1 plus 0i. So 0i, no need to write that, so it's just minus 1, right? So 8 pi, it's just minus 1. So minus 1 minus a minus ln of 8 0. This is just e to the power 0, right? So e to the power 0 is just 1. So 1 minus a, right? Now this is real part of minus I times log of minus 1 minus a divided by 1 minus a, right? Now at this point, we do need to like observe carefully what's going on. Now we are in the complex world, right? Like if you don't have the idea, like in real world, the log needs to have some positive numbers inside it, right? But in complex world, even if there's some negative numbers, like let's say minus 1, it's defined in the complex world, right? And yeah, So we can write -1 as e to the power I pi, right? So log and e cancel out, this is I pi. So you see that log of -1 is I pi. And this is basically just the principal value. There are other answers as well, which we don't need to consider here right now. So yeah, just wanted to show you that log is defined even for negative numbers in the complex world. So over here, now we need to see, okay, we need to see like if the values that log function is giving, if they are real numbers, right? For certain values of a, this will give real numbers. For certain value of a, this log function will give us complex numbers, right? Just like how over here this can be real as well as complex. We saw that, right? Now whenever it's real, that's going to be a real times minus I, right? A real number times minus I is a complex, is imaginary number. So in that case, the real part will of course be 0, right? Because the entire thing is imaginary number. So from here, what we saw that whenever this thing is real, our answer is going to be 0, because if this is real, minus I times a real number is imaginary number, so the entire thing is imaginary number, so there's no real part. The answer is going to be 0, right? And when this is like a complex number, when there's a complex number, if it has both real and imaginary part, now that imaginary part, when it's multiplied with minus I, then we will get some real part, right? So yeah, in this case, there will be some answer will be something, right? So now the problem is we need to, so we have to divide it into two cases. There will be answers, the answer will be 0 in some cases, there will be some answers in these cases, right? Now the thing that we need to do is we need to know when this log gives a real number and when this log gives a complex number, right? Now we know that for it to give a real number, this thing over here needs to be a positive number, right? And for it to give a complex number, this thing over here needs to be negative, right? So we know that condition, right? Now we will try to find out when is this fraction positive, and we'll try to find out when is this fraction negative. Again, for this to be positive, there are two cases. In the first case, we can have both of these numbers positive, right? In that case, the entire fraction will be positive. The next case is both of these numbers being negative, right? In that case also fraction will be positive, right? If both are negative or both are positive, then the fraction is going to be positive. Now let's try to solve for each case. Now in this case, we need to have -1 is greater than a, so a should be less than -1, as well as, not just this, there should be and, as well as there should be or over here, right? So in this case, both should be true, or we can have this case, right? Either of them is like a possible solution. Now and as well as there should be a should be less than 1, right? So the first condition gives us this solution: a should be less than -1 and a should be less than 1. So that implies if this both has to be true, obviously the common thing that, I mean, for both to be true, a should be less than -1, right? Because if a is 0, like this is not true, right? A is not less than -1. So the solution that this condition implies is that when a is less than -1, definitely both of this condition is true and the fraction is positive. So we got a solution, right? If a should be less than -1. Similarly, let's get a solution from this case, right? For this one, we should have -1, a should be greater than -1. Over here, a should be greater than 1, right? So both should be true for the fraction to be positive. And yeah, so this implies if both of this condition has to be true, definitely a has to be greater than 1, right? Because a is 0. Though this is true, this is not true, right? When a is 0, so a has to be greater than 1. So yeah, so for this fraction to be positive, either a has to be less than -1, then both of them will be positive, so the fraction will be positive, or a has to be greater than 1, so that both of them will be negative and fraction will be positive. So again, these two solutions are our possible solution, and this can be like written as commonly written as the modulus of 1 being greater than 1, right? We can write it in this way, because but here also modulus of 1 is definitely greater than 1, right? Because if a is less than -1, a is -2, -3, -4, such values, in which case the magnitude is greater than 1. In this case also that is the case, right? So yeah, so we got a like common result. Yeah, this can be summarized in this common way, I mean in a like way that captures both the solution. That means it's positive when modulus of a is greater than 1. So if you are like a student of SKU, you might recognize that this was the condition given in the problem as well, right? I was just trying to make sense of why that should be true, or why that case was given. Yeah. Now in this case, we'll go similarly. We'll go with similar approach. So for this to be negative, either one, this numerator is negative and denominator is positive, right? Because if they have different sign, that's going to be negative, right? Or the numerator has to be positive and denominator has to be negative. So if this is positive and negative, again that's a negative number. If it's negative and positive, again that's a negative number, right? Just the different signs should be there in numerator and denominator. Now if we solve this says that a should be greater than -1 and a should be less than 1. So a should be greater than -1, a should be greater than -1 as well as less than 1. So this is the solution that the first case gives us, right? So either this can be true, or like the solution can also be gotten from another case as well. So this says that a should be less than -1 and as well as a should be greater than 1. Guys, is this even possible? Can a be greater than 1 as well as less than -1? No, that's not possible. So this gives us no solution, right? Because that's not possible. We cannot have both of them at the same time. So yeah, so this case, so this second inequality, so only the first case gives us a like viable solution, and this can also be written as the modulus of a being less than 1, right? Because in both of the cases, the value magnitude of the a is definitely less than 1, right? So yeah, the solution for this case can be written as magnitude of a being less than 1. So if you are again asking a student, you might have noticed that this was given in the problem itself. So yeah, so this is the reason why it was given. Now we know that in this case, when magnitude of a is less than 1, this fraction over here is negative, right? Magnitude of a is greater than 1, this fraction over here is positive, right? Because that's how we have solved it. Okay, now let's try to do the problem. So the problem was real part of minus a, ln of -1 minus a by 1 minus a. We are over here, right? Now we have found out from all these experimentation, right? Experimentation that when modulus of a is greater than 1, ln of 1 minus a by 1 minus a is a real number, is real. So real part of minus y times I can just write this as some x plus 0 I. There's no imaginary part, right? Some x plus 0 I. Or you can just say that this is just real, like some real. There's the one who is checking will understand definitely. So there's some real number, and now minus I times real, that becomes some imaginary number. In the real part of imaginary number, like there's no real number, so this is just 0, right? So this is the answer for the first case. And now for all other numbers, I mean not for all others, and definitely also note that there's no solution at a equals to 1. When a is equals to a modulus of a is equals to, okay, wait, when a is equals to 1, modulus of a is equals to 1, even for both cases. So how we can see this is, like, you can also invert this fraction, right, if you remove the minus sign. So how we can see this is, when a is equals to 1, let me also discuss this case. Though our solution was asked for only these cases, right, let's also discuss this case. Now in this case, we can basically break the logarithm as minus I ln of -1 minus a minus ln of my again plus I ln of 1 minus a, right? So in this case, when it's 1, so ln of minus 2 is definitely defined, right? But this one over here, ln of 0 is not defined, so there will be no answer. Similarly, when a is minus 1, in that case ln of 2 is definitely defined, but this one will become 0 again, so ln of 0 is not defined. So in these cases there will be no answer. So that's why it was also not given in the problem, right? Okay, so okay, now let's go to this case. So basically, if we deal with these three cases, we are basically dealing with all the numbers that are possible, right? Okay, now in this case we know that this over here, we know that in this case, wait, okay, in this case we do know that minus 1 minus a by 1 minus a is going to be negative, right? Okay, so it's going to be negative, then we have to deal it in a different way. So now let's write that this is minus I. Let's try to break this. 1 minus a plus I times ln of 1 minus a. That's how we break it, right? Because there's minus sign, there's going to be plus. Now again, notice that we know this entire thing is going to be negative, right? But let's again try to like see it part by part. Now we know that in this case modulus is less than 1, right? So definitely this thing is positive, right? Even if a is, even if, I mean, this 1 minus a, 1 minus a is going to be positive, right? Because even if a is less than 1, or I mean 0.5, this will be positive. 1 minus 0.5, 0.5 is positive. Even if a is negative 0.5, that's going to be positive. So this thing over here, ln of 1 minus a, this is going to be real, right? So this is the only thing that will like contribute the imaginary part. So yeah, you saw that in this, even in this case, if you break them, so this again, the second part is definitely going to be a purely imaginary number, cause this part is going to be a real number, cause this part is going to be a positive number. So that's the entire like tree. So yeah, we saw that this will not contribute to any real part, because this entire thing is going to be imaginary number, cause this part is a real number, right? So yeah, this part will not contribute to any real number, cause this is imaginary number. So yeah, if you just break the real part function, we can definitely say that the real part contribution from this is just 0. So we just need to look at the real part contribution from the first one, which is negative 1 negative a, right? Now okay, now over here, say if a is like modulus a is less than 1, you can definitely see that this is always negative, right? Yeah, because even if a is 0.5 or negative 0.5, that's always negative. So what we will try to do is we will try to break this. We'll try to break this as ln of minus 1 times ln of 1 plus a. We can do that, right? Because we know that ln of ab, wait, there should be a plus sign. Yeah, there should be a plus sign. I'm sorry for that. There should be a plus sign. Yeah, we can do that because we know that ln of ab is just ln of a plus ln of b, right? Over here also, this is the same thing. This is just ln of minus 1 times ln of 1 plus a, right? So we just broke it into ln of minus 1 plus ln of 1 plus a. It makes sense, right? After we break again, this will just be a real part of minus I ln of minus 1 plus real part of minus I ln of 1 plus a, right? That makes sense, right? Again, notice that for the case where modulus of a is less than 1, 1 plus a is going to be positive, right? Because a is 0.5, then this is positive, minus 0.5, this is positive. So this part is real, the entire thing is imaginary because multiplied by I. So it's not going to contribute again. So the only contribution is from this thing, minus 1 plus this, again real part of this thing is just 0. The real part from this thing is just going to be 0. That makes sense, right, guys? Yeah. Now after that makes sense, now let's try to come with this one. Now we know that the minus 1 is just e to the power I pi, right? So log of e to the power I pi, log in the e, that seems to be cancel out, right? So this is just I pi. Now again, this is real part of I square is minus 1, minus 1 times minus 1 is plus 1. So real part of pi in the real part of pi, because pi is real number, that's just pi, right? And that's a really beautiful answer to have. So we finally found the answer, that when the modulus of a is less than 1, the answer is pi, right? So yeah, now if you have to summarize the answer, for the modulus of a greater than 1, the answer is 0. When the modulus of a is less than 1, the answer is pi. And when modulus of a is 1, the answer is nothing, right? So yeah, this is the solution. This was a really beautiful problem, and yeah, definitely complex number simplified this problem a lot, because without complex number it could have gone really complex. So this is it, and hope you enjoyed the solution. Hope it was helpful, and hope just I like made everything really clear. Hope there are no doubts. If there are, you can definitely comment on the video, and I will try to answer them. So hope you're having a good time, and I look forward to seeing you in the upcoming videos too.